In this video, we'll discuss Borel and Radon measures, which constitute the majority of measures we'll work with in this course. So, given the metric space X, we say the Borel sets are the smallest sigma algebra containing the open sets. So, in other words, this sigma algebra contains all countable intersections of open sets, then all countable unions of intersections of open sets, all complements of these sets, and so on and so forth. So basically any set that we can construct from open sets using simple operations like countable unions, intersections, and complements. Then a measure is said to be Borel if all Borel sets are measurable. So to motivate why this class of measures is important, let's consider the following question. Given a measure, how do we know what its measurable sets are? Well, notice that if I have a smaller class of sets that I can verify are measurable, then all countable unions and intersections will also be measurable, and so will the unions and intersections of all these sets, and so on. And in fact, the smallest sigma algebra containing these sets will necessarily be measurable. Now, in this class, we're primarily going to be concerned with measures for which open and closed sets are measurable, and thus those measures will be automatically Borel. Now, often we might be proving a theorem that works for a nicer class of sets, like Borel sets or open or closed sets, but we want to extend it to more general class of sets. This leads us to the concept of regularity, which concerns being able to approximate a set in measure by a set from a nicer class. So one type of regularity is Borel regularity. So a measure is Borel regular if we can contain any set inside a Borel set of the same measure. In fact, Borel regular measures are also irregular with respect to closed sets, meaning that we can approximate any measurable set from within by closed sets. A smaller class of measures that have even better regularity properties are the Radon measures. So a measure is Radon if, first of all, it's Borel regular, it is finite on compact sets, it's irregular on open sets. So this means that for any open set, the measure of the open set is equal to the supremum of the measures of all compact sets contained in it. And finally, it's outer regular on all sets. So given a set A, it's equal to the infimum of measures of all open sets containing it. Okay, so far these definitions have been quite abstract. So one can check in an ad hoc fashion that certain measures are Borel regular, but later we're going to start constructing measures in a very general fashion, and we need a way of telling whether or not they are Borel regular or Radon. So for the rest of this video, we're going to focus on some of the main ways that we deduce the regularity of a Radon measure or construct Radon measures. One condition that will be quite easy to check when we construct Hausdorff measure later on is whether a measure is a metric outer measure or not. So a metric outer measure is a measure that is additive on sets that have positive distance apart from each other. And this theorem says any metric outer measure is a Borel measure. Now that we have a test for being Borel, how do we know when a measure is Borel regular? Well, later on when we construct Hausdorff measure, this will actually be implicit from the construction, so we won't worry about giving a sufficient condition here. However, given a Borel regular measure, how do we get a test for being Radon? Well, the only difference between Borel regular measures and Radon measures, at least in complete separable metric spaces, is just about local finiteness. Recall that now that we have a test for being Borel, how do we know a measure is Borel regular? Well, later on when we construct Hausdorff measure, this will actually be implicit from the construction, so we won't worry about giving a sufficient condition here. However, given a Borel regular measure, how do we get a test for whether or not it's Radon? The only difference between Borel regular measures and Radon measures, at least in complete separable metric spaces, is just about local finiteness. A measure is said to be locally finite if every point is in an open set of finite measure. If we're working on a complete separable metric space, then the Radon measures are exactly those locally finite Borel regular measures. So what if we have a Borel regular measure that's not locally finite? So one thing to observe is that if we restrict a Borel regular measure to a measurable set, then it is still Borel regular. So thus, if we are given a Borel regular measure that isn't locally finite, we can restrict it to a set of finite measure to get a Radon measure. So for example, consider counting measure. This is a Borel regular measure. It's Borel simply because all sets are measurable, and any set of finite measure is a finite union of points, which is a Borel set, and so it must be Borel regular. However, it's not locally finite in any Euclidean space, since any Euclidean ball has infinitely many points. However, if we restrict to a discrete set, then this is a Radon measure, since discreteness implies no ball contains infinitely many points, and so counting measure will be locally finite on this set. Another way we'll often generate Radon measures is by pushing one measure onto another space using a function. So given a function between two metric spaces x and y, and a measure on x, we define the push forward, or image measure of mu, denoted f bracket mu, to be a measure. We define it by setting the measure of a set A in Y equal to the measure of its pre-image under F. So it's not hard to show that this defines a measure. With some more work, one can show that if F is a Borel function, meaning the pre-image of any Borel set is also Borel, and that mu is a Borel measure, then the push forward of F is also Borel. Now, for the Radon property to be conserved under image measures, we also need the metric space to be separable and for X to be compact. Now, one useful property of push-forward measures is the following identity that we'll be repeatedly using in this course. It's essentially a change of variables formula, which says that the integral of a function with respect to the push-forward under f is the same as the integral of the composition of that function with f with respect to mu. Finally, a more abstract but very convenient way for generating Radon measures is the all-familiar Riesz representation theorem that you should have seen in your measure theory or functional analysis course. So given a locally compact Hausdorff metric space and a positive linear functional on the space of continuous functions vanishing at infinity, there is a Radon measure such that the linear functional evaluated at f agrees with the integral of f against this measure. This is a very amenable method for constructing Radon measures, and we'll demonstrate one example of how to use it in the next video when we study limits of measures.